Einstein, on the Principle of Relativity. By Albert Einstein and Harry Yoon, Translator. Foreword by Translator. When a man sits with a pretty girl for an hour, it seems like a minute. But let him sit on a hot stove for a minute, and it's longer than any hour. That's relativity. Albert Einstein. Of course, that is not relativity, but Einstein was a joker. He was indeed a down-to-earth, genuine human being. If you are interested in getting a high-level overview of relativity, in particular special relativity, then this booklet is for you. This short article was originally written by Albert Einstein in 1914 at the request of the Vossische Zeitung, one of the most widely read newspapers in Germany at the time. This was one of the very first articles written by Einstein for the general, non-scientist audience. Einstein published his two seminal papers on special relativity in 1905, and his work was gradually being recognized. In 1913, Max Planck and Walther Nernst, two of the most prominent scientists of that generation, made a trip to Zurich, Switzerland, where Einstein had been living for most of his young adult life, in order to recruit him back to Germany. It was a triumphant return for Einstein. Einstein became a member of the Prussian Academy of Science and a full professor of Berlin University, with no teaching obligations, which enabled him to continue to work on general relativity, his next ambitious project. This article was published to celebrate this occasion and his newly earned prestige. Special relativity was, in many respects, one of the most radical scientific theories in history. Special relativity is based on the special principle of relativity, or simply the principle of relativity. This short article explains what the principle of relativity is, at a very high level, and what kind of general interesting phenomena are predicted from the theory. One of the most significant consequences of his theory of special relativity was the principle of mass-energy equivalence, that is, E equals mc squared, which is probably the most well-known equation in science, possibly only after the Pythagorean formula. As for general relativity, Einstein allocates the last one paragraph in this newspaper article. Interestingly, as of this writing in 1914, Einstein thought he had the final solution, but as it turned out, it was not the correct one. The correct gravitational field equations, now known as Einstein's field equations, were finally published in November 1915. This article was originally written by Einstein in German, and it is now in public domain. This short booklet attempts at a new translation to give a somewhat clearer account of what Einstein wanted to convey in his original writing. Note: the article is organized into 6 small sections in this translated version. This division did not exist in the originally published form. On the Principle of Relativity. Prologue. The editorial staff of the Vossische Zeitung has requested me to write something from my area of research for their readers. I gladly accept this request. This is a great opportunity for me to share a little about the theory of relativity with the general public. Although a deeper understanding of the theory is not possible without putting in some level of effort, it may still be of interest to the non-scientist reader to briefly hear about the methods and results of this new branch of theoretical physics. The special principle of relativity. We are all familiar with the common physical process that we call motion. From everyday experience, we already know that we can only perceive relative motions of things with respect to each other. Let us suppose, for example, that we sit in a car of a railroad train and see another train pass by, say, on the neighboring track. If we disregard the vibration of our train for argument's sake, then we have no immediate way to find out whether the two trains are, or which of the two is, really moving. We can only say, from our visual perception, that the relative position of the two trains changes over time. Even if we now pay attention to various objects next to the track, such as the signs and telephone poles that are fixed on the ground, the essential point of this argument remains the same. We usually view the objects like the telephone poles, as well as the surface of the Earth, to be stationary, or at rest, and we refer to all other objects which change positions relative to them to be in motion or moving. But when we do this, we are merely relying on our customary way of thinking and casual manner of expression, which have no fundamental significance. As a matter of fact, an observer who is in a moving train car will be perfectly justified if he says, from his own vantage point of view, that the train is at rest and the ground and telephone poles are in motion. Physicists have ultimately found that this characteristic of motion, i.e., appearing to be entirely relative, is not merely a result of our rudimentary perception, but rather, it is an inherent property of nature. From the viewpoint of physical laws, we are indeed justified to consider any single object to be at rest, among a myriad of objects in the universe, which are in uniform motion relative to each other. To be concrete, let us imagine once again that we are in a car of a train, which is traveling uniformly and steadily on a straight and level track. The train ride is assumed to be absolutely smooth so that there are no detectable vibrations in the car, coming from the train wheels or railroad tracks. We further assume that all windows are tightly shut so that there are no air or light coming in. Inside the train car, there is a physicist with all kinds of laboratory apparatus, and she is ready to do any experiment that we can possibly think of. Now, due to the relative nature of motion, we already know that all experiments to be done by this physicist will produce exactly the same results as if the train were not moving, or for that matter, if the train were cruising at a completely different speed. This statement is, in essence, what we physicists commonly refer to as the Galilean Principle of Relativity, e.g., in the context of classical mechanics. This principle can be more precisely phrased in a more general manner, as follows. The laws of nature that are perceived by an observer are independent of the state of motion that the observer is in, as long as all observers are in uniform relative motion relative to each other, Galilean observers. This is the special principle of relativity, which should hold with regard to all fundamental laws, and not just the laws of mechanics, for instance. The special theory of relativity is based on this universal principle. Crisis in old physics. This statement sounds innocuous enough, and it does not seem to require any further explanation. It would not have drawn anybody's attention, in fact, if it were not for the latest controversy. The laws of propagation of light, which have emerged from the more recent advances in Maxwell's electrodynamics, turn out to be incompatible with this seemingly obvious and time-tested principle. On the one hand, many experimental results in electrodynamics and optics of moving bodies inevitably lead to the conclusion that light in a vacuum always travels with the same constant speed, conventionally denoted as c, irrespective of the state of motion of the observer or that of the source of the light. On the other hand, however, this logical conclusion, which is directly based on the empirical findings, seems to be in clear conflict with one of the fundamental hypotheses in physics, namely the aforementioned special principle of relativity. We can easily see this apparent inconsistency from the following simple arguments using a self-contradictory example, which involve both mechanics and optics. Suppose that there are two Galilean observers, A and B, and the second observer B is uniformly moving at a constant non-zero speed v greater than 0 in a certain fixed direction, say, to the east, relative to the first observer A. Now the observer A observes that a beam of light is transmitted in the same direction with the universal light speed c, naturally. Then, from the viewpoint of the same observer A, the light beam should propagate at a smaller speed than c, with respect to B, since the second observer himself is moving in the same direction with the speed v. That is, the speed of light relative to B should be, or should appear to A to be, something like c minus v, which is less than c. This is because velocities are additive in classical mechanics. But this cannot be true, since if this were really the case, then the law of propagation of light in a vacuum would not be the same for the two observers who are in a uniform motion relative to each other. That would be a contradiction to the principle of relativity stated above. In fact, it must be the case that the second observer B also sees the beam of light propagate at the same universal light speed c. Furthermore, the speed of light with respect to B, seen by A, must be the same c as well. There was definitely a conflict between the law of the constant speed of light and the special principle of relativity. This conflict could not be explained in the framework of classical physics. Special relativity. This is where the theory of relativity comes into play. This theory demonstrates that the law of the constant speed of light in a vacuum can indeed be satisfied for two Galilean observers at the same time, who are in uniform relative motion with respect to each other. That is to say, according to this new relativity theory, the same beam of light is observed to have the same speed of propagation, c, by both observers, regardless of whether and at what speed they are moving relative to each other, or relative to the surface of the Earth, etc. At first, this kind of perfect resolution appears impossible for such a paradoxical inconsistency. But the resolution has been achieved, in particular, through a comprehensive analysis of the very physical meaning of the spatial and temporal information. What is especially important in the context of solving this paradox turns out to be recognizing the relativity of the concept of simultaneity. Until the theory of relativity was generally accepted, it was believed that the statements like two events happened at two different places at the same time, simultaneously, had a clear and self-evident meaning, which did not require a precise definition of the conception of simultaneity. However, a more careful investigation, which did not circumvent the issue of the physical meaning of simultaneity, showed that the simultaneity of two events was not absolute, but rather, the concept of simultaneity could only be defined with reference to a particular observer in a particular state of motion. As it turns out, two events which are simultaneous with respect to one Galilean observer are in general not simultaneous with respect to another Galilean observer who is uniformly moving relative to the first one. This represents a fundamental change in our idea of time, including the concept of now and the concepts of the past, the present, and the future. This is the most important and yet probably the most controversial theorem of the new theory of relativity. It is not possible to get into an in-depth discussion here on its epistemological and metaphysical assumptions and the consequences that emerge from this basic principle. Those who want to learn more about special relativity can consult any of the standard textbooks on this subject. If we combine the principle of relativity with the law of the constant speed of light in a vacuum, then we are led using a purely deductive method to what we call today as the special theory of relativity. As an important tool for the theoretical deduction of the laws of nature, this theory has already proven its value in the area of fundamental physics. In particular, its significance lies in the fact that it provides the stringent conditions that every general law of nature must satisfy. This is because, based on this theory, the fundamental laws of nature cannot depend on the state of motion of the Galilean observer in relation to who the phenomena in question are referenced in space and time. Consequences of special relativity. Out of the many important results of the special theory of relativity, the following two will be mentioned here. They may be somewhat interesting to the layperson. First, the hypothesis of the existence of a space-filling medium for light propagation, the so-called luminiferous ether, should be regarded as unnecessary. According to this new theory of relativity, it is no longer the case that light appears as a state of motion of a hypothetical carrier, e.g., in the similar way that a sound wave emerges as vibrations of air, but rather as a physical structure with a physical existence of its own. Second, the theory establishes that the inertia of a body, or its inertial mass m, is not an absolutely invariant constant, but rather that it grows with the body's energy content, E. That is, E equals mc squared. The two important theorems of conservation of mass and of energy, respectively, now fuse into a single conservation theorem. The energy and the relativistic mass of a body, which is determined by its energy, are not separately conserved. It is the rest mass, or just mass in modern terminology, that truly remains constant even in the relativistic realm, that is, when the bodies are moving fast compared to the speed of light c. General relativity. Now the natural question is is the special theory of relativity described above essentially done or complete? Or is it just a first step and a further development is necessary? Over this question, physicists who value the theory of relativity split in their opinions. Nevertheless, some important considerations seem to guide us to the second alternative, which I present next. In the above, we have stated that the laws of nature are exactly the same for a uniformly moving observer, e.g., a person on a moving train, as they are for an observer at rest, e.g., a person on the ground. They are all Galilean observers in our terminology. That is to say, it is impossible for an observer to find an evidence which will allow him to determine whether he is at rest or in a state of uniform motion in reality. The stationary and uniformly moving states are physically equivalent. Hence, it is now important to know whether the principle of relativity is only limited to uniform motions. Couldn't the laws of nature be such that they are the same for two non-Galilean observers who are in arbitrary, e.g., non-uniform and non-rectilinear motion relative to each other, the general principle of relativity? It has become clear in recent years that such an extension of relativity theory can be indeed carried out, and that such an attempt leads inexorably to a generalized theory of gravitation, which contains the good old Newtonian gravity, i.e., the inverse square law, as a first-order approximation. According to this general theory of relativity, rays of light should bend in a gravitational field. Although the curvature or the degree of bending may be rather small, it seems just within the reach of astronomical measurement at this point, e.g., by measuring bending of starlight near the sun during a solar eclipse. The future will teach us whether this generalized relativity theory, which is very appealing from an epistemological point of view, conforms to reality. Albert Einstein, April 1914. Afterword by Translator. Albert Einstein is probably the most well-known physicist in history. The name Einstein is almost synonymous with genius. In truth, however, Einstein was anything but a genius in the traditional sense. Einstein dropped out of high school, and he initially flunked a college entrance exam. He had to go to a community college for 1 year before he was formally accepted to the university in Switzerland, now called the ETH. After graduation in 1900, he couldn't get a teaching assistant job. No professors had a high opinion of him. Thanks to one of his best friends, he finally got a job at the Swiss Patent Office. In this period, completely outside the mainstream physics, his creativity blossomed. The year 1905 is called Einstein's miracle year. All 4 papers published in that year changed modern physics in a profound way. Einstein never did well in the system. He was free-spirited and even anti-authoritarian. Einstein was a true rebel, just like Galileo was some 300 years before him. Einstein, if he had been born in modern times, could never have done well in the current environment of physics, where knowledge is regarded more important than true understanding, and where the equations triumph true physical insight. Physics originally started as a branch of philosophy. The original physics was called cosmology, e.g., science of the cosmos. The word physics was first coined by Aristotle, who had a profound influence on the development of physics for the following 2 millennia. Since the scientific revolution in the 16th and 17th centuries, physics was gradually becoming separate from and independent of philosophy. Physics is now a completely empirical science with no room for philosophical musings. Very few physics students learn philosophy. Most of them do not even know what the words like epistemology or metaphysics mean. However, Einstein was more of a philosopher than physicist. It is well known that he was deeply influenced by Immanuel Kant in his youth. Although he might not have considered himself a philosopher, if you read any of his writings, including technical papers, you cannot help but wonder what he was. Modern physics currently faces a lot of challenges, especially in the foundations of physics. We do not even have to use the word like crisis. But nobody understands what time is, for example, or even what space is, at a fundamental level. The foundations of quantum mechanics, the most successful branch of physics in the 20th century, are still shaky. How do you reconcile the fact that the quantum world is non-local, and yet we are undoubtedly living in a world where locality, however you define it, is so fundamental, which Einstein rather passionately believed? We need some new generation of young and old physicists who can take modern physics back to its root, philosophy. We are waiting for the next Einstein.